When there's been an unexplained structural or mechanical failure, the first thing that most investigators want to look at are the design calculations and the design analyses. And these can often provide an immediate clue as to why the failure occurred. Now, there's been dozens of videos produced on the OceanGate Titan implosion, but the one thing which I don't think anyone has looked at is how the hull was designed in the first place. And that's what I'm going to do today. And this has only been made possible by the publication of the analysis report through the US Coast Guard hearings which took place last year. The report I'm referring to is the one which was prepared by Spencer Composites back in 2015. They had a design and manufacture contract for the first composite hull, although this wasn't actually the hull which failed, which was manufactured by Electro Impact. However, we have no evidence that the report was updated to reflect any difference between the two hulls. Now we have here the design basis in tabular format. We've got two columns here, what they call the optimum, which I take to mean the target value, and the limit, which I think is the minimum acceptable value if the target can't be achieved. And the values at the top have all been specified by OceanGate, and the values at the bottom have been specified by Spencer Composites. So you see we're aiming for a maximum operational depth of 6,000 metres, and you'll note that the Titanic is actually only at 4,000 metres, and this with a factor of safety of 2.25. And we're aiming for 10,000 dive cycles with a minimum acceptable value of 1,000 dive cycles. And this equates to a design external pressure of 9,000 psi or 60 megapascals with a collapse pressure of 20,000 psi, which is 9,000 psi multiplied by a factor of safety of 2.25. And clearly, if we can achieve all of this, we've got a hull which will meet all relevant design requirements. So what did they do? Well, as expected, they did a detailed finite element analysis of the hull. And this is because the FE method is by far the most powerful and most widely used analysis method. But the computational requirements can be very high, and these analyses can be very onerous. And so Spencer Composites sought to make economies where they could. And instead of doing a huge three-dimensional analysis of the complete hull, they made the assumption of asymmetry. Now what this means is that at any cross-section through the hull, you assume that the stresses and strains are identical all the way around the circumference. And I'll come on to this assumption later. But the bottom line is, instead of doing a detailed three-dimensional analysis, the model reduces to 2 dimensions with a huge reduction in the computational requirements. And furthermore, because of the symmetry of the hull about the central cross-section, they've only had to analyse one end of the hull. Overall, a very economical approach, and certainly completely justified for the initial analysis. So let's talk about the form of construction of the carbon fibre hull and the associated modelling. Now, the basic units are the longitudinal plies, which are formed by a single layer of pre-preg carbon fibre, and these are about 0.8 millimetres thick. And they, in accordance with the overall stress distribution, they go 2 for 1. So for each horizontal ply, they got 2 going circumferentially, and these are about 1.6 millimetre thick. And each lamina is modelled by a single layer of finite elements. With this form of modelling, each element only has plies running in a single direction. And the compliance matrix, which gives the relation between the strains and the stresses, takes this form. I do assure you that if you have fibres running in more than one direction, this becomes infinitely more complicated. And if you know the mechanical properties of the carbon fibres and of the resin, you can synthesize the elastic properties which you need for the analysis. So here, for example, we've got the elastic moduli. Here we've got the Poisson's ratios, and here we've got the shear moduli. And if you count it up, you'll find that you've got 6 independent values. We've got the relevant material properties to perform the analysis, but at what point is carbon fibre going to fail? Unfortunately, we don't have adequate test data for these selected materials. So what they've done is they've gone to a US military document which was prepared in the early 1990s, which has a database of test results. They've extracted relevant data and averaged it, and they've come up with a failure stress of 214 KSI. But they then argue that material properties have been improving over the years, and you can add 15% to it. And so they quote failure stress of 246 KSI, which corresponds to a failure strain of 9,400 microstrains. They furthermore go on to argue these failure values are applicable in areas of uniform compression, such as on the centre line of the hull, but that if the highest compressive stress is reduced because there's a bending element, that you can take higher failure values. And they quote a failure stress of 325 KSI and failure strain of 14,000 microstrains. And they argue that this value should be used at the interface between the carbon fibre and the titanium ring. They furthermore say that this was used successfully by Spencer Composites for Steve Fossett's Hawk's Ocean Technology Deep Flight Challenger hull. Well, that sounds very impressive, but to the best of my knowledge, this hull has never been used and has never been pressure tested, so I'm not sure how you can claim that it was used successfully. Whilst it's assumed that the carbon fibre acts elastically up to the point of failure, full material nonlinearity is modelled both for the titanium endomes and for the adhesive. And furthermore, geometric nonlinearity is assumed, so the change in the geometry of the hull as the loading is applied is modelled. So to summarise, they've done a detailed nonlinear analysis of the hull and the endomes using axis-metric elements. Now, using axis-metric elements, it will give good information about what's happening at the interface and through the thickness of the hull, and it will also pick up any buckling in the axial direction, but it can't model hoop buckling, and this will need to be studied separately. For the material properties, they've used third-party data from a database which was compiled about 30 years ago. They've applied their own correction factors, and this is okay for the preliminary analysis. However, as you get into detailed design, you'll need to make up test specimens using the actual selected materials. And beyond that, when the hull itself is manufactured, you need to take test specimens from the offcuts at the end of the hull. So let's look at the results for the carbon fibre hull. Now, what they've done is they've applied an external pressure of 9,000 psi, which corresponds to a dive depth of 6,000 metres, and they've computed the strains at all points through the model. And they've compared this to the estimated failure strain to compute a factor of safety. And if we look at the hoop direction, the highest strains are on the centre line of the hull on the inner surface, the area depicted in blue. And with their definition factor of safety, they compute 2.19. Well, given that the dive depth down to the Titanic will only be 4,000 metres, this implies a factor of safety of 3.3. In the axial direction, the highest strains are at the other end of the hull at the interface with the titanium ring, again shown in blue on the centre core of the hull. Now, if you recall, they argued that the failure strains in this location are going to be higher, and on that basis the computed factor of safety is higher, and hence it doesn't govern. So that's it then. When we dive down to the Titanic, we've got a factor of safety of 3.3 against static collapse. Job done. No wonder Stockton Rush was going around saying that inside the Titan semi-sub it was going to be, as I recall, the safest place on Earth. So what we have is a detailed analysis report prepared by an expert consultant saying we've got a factor of safety of over 3 against static collapse if we dive down to 4,000 metres. And that's clearly not what happened in practice. There's a huge disconnect between theory and practice in this case. So what I'm now going to do is I'm going to deconstruct the work that was done. I'm going to start at the bottom and work my way up, and by the end I'll really be swinging the axe. So let's start with a humble title block. And if you've seen other videos on this channel, you'll see it's amazing what information you can get from this. Now, any title block, it should firstly indicate who prepared the document, who checked it, who approved it for issue. It also needs to indicate what the purpose of the issue is, and finally it needs to have a revision history. Now, looking at this document, there's only one column, and that's got the signatures of the big guy himself. And just because the big guy seems to have prepared it doesn't mean that it doesn't have to be checked and it doesn't have to be approved. Nothing changes. You also note that there's no indication as to what the purpose of the document is, and it should say preliminary, not for construction. And there is a revision history, but there's one very important revision which is issuing. And the first time it goes to the client should review it. He needs to put it on IDC, which is interdisciplinary checking, needs to go around the engineering department. Everyone adds their own comments, goes back to the engineering manager. He collects the comments, sends them back to the consultant who reviews them, and he amends the document and reissues it as necessary. I got a horrible feeling that the dysfunctional OceanGate engineering department didn't even bother to review it. Document came in, job done, that's fine. Next point, what software was used for this analysis? Now, there are huge, all singing, all dancing software systems used in the industry with names like ANSYS, Adina, Abacus, Nastran, Mark, and they're very capable. They're fully quality assured and they've been proven by thousands of test cases, and you can have confidence in the results. But they are expensive, and you can easily pay tens of thousands of dollars per year for one license. And when you write an analysis report, you say, we use Abacus, and that's a mark of prestige and respect. But this report's completely silent on what software was used, and it makes me wonder if they didn't in fact use some cheapskate software system, maybe written by a PhD student, but completely unQA'd and undocumented. Very odd. But there's a second piece of software which is also integral to this, and that's the software which is needed in order to generate the material properties to go into main analysis. And what they say is we use the methods of reference 6. Now, if you look at reference 6, this contains very detailed, intricate equations, and coding this up, I can say from bitter experience, very demanding, so easy to make errors. And this piece of software is much more likely to be proprietary in-house. And what they need to do is they need to show a user manual, a theory manual, quality assurance manual. That needs to be referenced in the analysis report. And they're completely silent on this. And it means it's completely impossible to check what they've done and to QA it. Not good. And whilst on subject quality assurance, it would help if they showed displaced shape plots, if they reported stresses rather than strains, and if they reported these support reactions. It would make it much easier to verify the results. However, my little hand calc here predicts maximum strains on the inner surface of 4,000 microstrains compared to their number of 4,200, and on that basis I'm not worried that there are any basic errors. Now, the next subject is very important, and it's how they've computed the material failure in the analysis. And this falls into two parts. The first one being the assumed strength of the material. Now, because they didn't have actual test data based on production samples, Spencer Composites went to a publicly available database. They did their own desktop study and they came up with failure stress, failure strains, and the highest number they used was 325 KSI, and that was for the axial failure stress in the hull. Now if you have a look at the database, you see there's a wide range of test examples included, all tested failure under either uniaxial tension or uniaxial compression. But if you look at some of the data sheets, you see very much lower numbers. So taking one at random here for an AS4 unidirectional carbon fibre laminar, and there's a range of failure stresses, and the low number being 176 KSI, and that's about 55% of the value which Spencer Composites use for design. So my first question is, how did Spencer Composites decide which values to use? Did they merely select the data which gave all the high numbers? But the second point, you never ever use the mean failure stress when you're characterizing a material. What you do is you compute what's called the characteristic strength of the material, and this is almost always defined as being the mean minus 2 standard deviations. It means that 97.5% of the values will lie above the characteristic strength, but 2.5% will lie below, and this is taken care of through the safety factor. So I have huge questions about the failure stress assumed by Spencer Composites for design purposes. Well, we've measured the failure stress, failure strain under uniaxial loading, but what guarantee is there that this number will also predict failure in real world conditions with much more complicated stress situations? There is no guarantee. Composite materials are complicated and they've got a number of individual failure mechanisms, any one of which can cause final failure. And for this reason, a number of failure models have been proposed which try to look at these individual failure mechanisms. And I show you here one such model, widely used, the Hoshin model, and this is as programmed into Abacus. Now this model works very well under certain conditions, but much less well under other conditions. And there's a number of other competing failure models, and they're much the same. And for this reason, some years ago, there was a worldwide failure exercise, and the organisers made available properly documented lab test results, and the individual researchers were invited to benchmark their failure models against the actual test data. And there were 20 test cases which were made available, and some 12 or 13 individual models. Now we show the results here in tabular form, and where there's a green square, it meant that theory and test data agreed to within 10%, but the red squares, they were out by more than 50%. And there's an awful lot of red squares, aren't there? And I can assure you that all of the failure models were much more sophisticated and advanced and simply using the uniaxial failure stress. So I think for Spencer Composites to use this criterion without any justification or benchmarking, completely unjustifiable. I personally have zero confidence in the computed failure load from the analysis report. We now get to what I consider to be the nub of the matter, and that is that the designers decided ahead of time how the hull was going to fail by static collapse without buckling. They put all their efforts into looking into this, and they didn't even consider other failure modes. Now it's not for the designers to decide how the hull is going to fail, the hull will decide that for itself. Now some of these other failure mechanisms, or what we call ultimate limit states in engineering, these include various types of global buckling. You've got local buckling, you've got material breakdown under repeated loading, you've got material degradation under environmental effects, you've got creep, you've got local mechanical damage, and no doubt 2 or 3 more which I haven't even thought of. And all of these need to be looked into individually. Now I'm not going to speculate about how the hull actually failed. Plenty of others have done that. But I will point out the obvious facts that the hull did survive a number of dives down to 4,000 metres, albeit I think with a very much reduced safety factor compared to what the passengers thought, and that it failed on subsequent dive. So clearly there was some form of degradation ongoing. Now the design criteria said that the hull should be good for 10,000 dives. The designers didn't even look into this, nor did they mention this omission in their final report. So what was needed was a structured and comprehensive program technology development to get to the bottom of all of these issues. And this needed to be conducted under documented protocol, such as the building block approach, which is used by the US military in developing composite structures for military aircraft. Now this would have taken at least a couple of years, and it would have required money which is way beyond OceanGate's resources. In summary, Spencer Composites produced a preliminary report and came up with their estimate of the factor of safety of the hull against collapse. I think the report was very amateur. I think they made a number of very dubious assumptions, and I think that their predictions were very optimistic. But for me, the biggest error was in their report. They didn't highlight all of the assumptions and all of the things they didn't look at, and it made it easy for the client to misuse the report. On OceanGate's side, they accepted the report unquestioningly and with open arms, because apparently it gave them the answer they were looking for, and I think they genuinely convinced themselves that the hull was super strong and had been designed conservatively. To me, this was yet another blot on the reputation of their appalling engineering department. For those of you who are interested in knowing more about this subject, I would recommend reading these two excellent review papers, both of which are available for free on the internet.